Two important theories have been developed to explain the properties of acids, bases, and salts. These are the Arrhenius theory and the Bronsted-Lowry theory. Here we'll look at the Bronsted-Lowry theory. This theory of acids was proposed independently in 1923 by two people, Johann Nicholas Bronsted, a Danish chemist, and Thomas Martin Lowry, an English chemist. We'll introduce the main points of this theory. Before we do that, just a quick word here about a hydrogen atom. Its atomic number is 1, so it has 1 proton. A neutral hydrogen atom also has 1 electron. It is known that over 99.98% of the hydrogen atoms on Earth contain no neutrons. So we'll state here that a hydrogen atom has no neutrons, which is nearly always the case. If 1 electron is removed from a hydrogen atom, it forms an H+ ion. Here's the equation showing that. A neutral H atom has 1 proton and 1 electron. So removing an electron will leave a charge of positive 1, 1 proton, and 0 electrons. So an H+ ion contains no electrons, no neutrons, and 1 proton. Therefore, an H+ ion is the same thing as 1 proton. Or we can say that H+ equals 1 proton. We use the terms H+ ion and proton interchangeably in Chemistry 12. According to the Bronsted-Lowry theory, an acid is any species that donates a proton or H+ ion to another species. Let's look at an example of this. Let's start with a molecule of hydrogen chloride, HCl, and a molecule of water, H2O. Here are the Lewis structures for these molecules. HCl is a polar molecule. There is a partial negative charge on the chlorine atom and a partial positive charge on the hydrogen atom, shown by the delta minus and delta plus. The water molecule is also polar. The oxygen atom has a partial negative charge, and each hydrogen atom has a partial positive charge. The negative charge on the oxygen pulls the partially positive hydrogen atom away from the chlorine. The hydrogen leaves its shared electron with the chlorine atom. The chlorine atom has gained an electron, so it acquires a negative charge and becomes a Cl- ion. The hydrogen atom lost an electron, so it acquires a positive charge, forming an H+ ion, which is also called a proton. The proton moves to the water molecule and attaches to one of the lone pairs. Instead of staying with the hydrogen atom, the positive charge is considered as the charge of the whole ion, so we'll move it over here. There are now 3 H atoms attached to one O, so the formula is H3O instead of H2O. We'll draw square brackets around the H3O because it's an ion, and write the positive charge here in the formula. Chemists call the H3O+ ion the hydronium ion. So we can summarize the whole process here. We started with a molecule of HCl, and we added a molecule of water, which gave us an H3O+ or hydronium ion plus a Cl- or chloride ion. We can now write an equation to show this process. We write HCl gas plus H2O liquid forms H3O+ aqueous plus Cl- aqueous. We can also represent the process like this. This shows an H+ ion or proton is being transferred from the HCl molecule to the water molecule. So this is called a proton transfer. H2O has gained 1 proton, so it forms an H3O+ ion. HCl has lost 1 proton, or H+ ion, so it forms a Cl- ion. Because the HCl is losing or donating a proton, according to the Bronsted-Lowry theory, it is called an acid. To indicate this, we often call it a Bronsted-Lowry acid, or Bronsted acid for short. According to the Bronsted-Lowry theory, a base is defined as any species that gains or accepts a proton, or H+ ion, from another species. Because the H2O is gaining or accepting a proton, it can be defined as a Bronsted-Lowry base, or Bronsted base for short. So in this reaction, HCl is an acid and water is a base. Because the reactants HCl and H2O are not ions, but the products H3O+ and Cl- are ions, We call this process the ionization of HCl. Here's a question. We're asked to write the equations for the ionization of the following acids when they're added to water, and to identify the acids and bases on the reactant side. We'll start the first reaction by adding liquid water as the other reactant. The formula for this compound starts with an H, so we assume it acts as an acid, and we'll label it as an acid. So the other reactant, water, must act as a base in this case. Now an acid is a proton donor, and a base is a proton acceptor. So that means a proton, or H+ ion, will be transferred from the acid HNO3 to the base H2O. So this means that water will gain an H+, which is one H and one positive charge. Adding an H and one positive charge to water gives us H3O+, the hydronium ion. The acid HNO3 has lost one H+, which means it has lost one H and one positive charge. We remove the H atom from HNO3, giving us NO3, and taking away one positive charge is the same as adding one negative charge. So we have NO3-, the nitrate ion. Both of the new ions formed are aqueous. So this is the equation for the ionization of HNO3. HNO3 is the acid on the left side, and water is the base on the left side. Now we'll see what we get if we add HCN to water. Because HCN starts with H, we'll treat it as an acid, and H2O is a base. So there will be a proton transfer from HCN to H2O. The H2O will gain a proton, or H+, and form H3O+, or hydronium. And the HCN will lose a proton, or H+, and form Cn-. So this is the equation for the ionization of HCN. HCN is the acid on the left, and water is the base. A double arrow is used here because the ionization of HCN does not go to completion. In a solution of HCN, only a few molecules are ionized. You'll be shown how you can tell whether to use a single or double arrow later in the course. Now let's consider this reaction. Again, the double arrow here just tells us that this reaction does not go to completion. Instead, an equilibrium exists here. We see that the NH3 has been converted to NH4+. In doing so, it gains one H and one positive charge. Therefore, it gains one H+, or one proton. Because it gains a proton in this case, the NH3 is classified as a base. Looking at water, we see it has been converted to OH-. OH- has one less H and one less positive than H2O. Therefore, it has one less H+ than H2O. Therefore, when H2O converts to OH-, it loses an H+, or proton. For that reason, we identify H2O as an acid in this case. Now we'll look at the previous reaction we had in which HNO3 reacts with water. In this reaction, water acted as a base. So we can now see that, depending on what it's reacting with, water can play the role of an acid or the role of a base. Such a species is said to be amphiprotic. An amphiprotic species is one that can act either as an acid or as a base depending on what it's reacting with. Water is one amphiprotic substance. There are many more, as we shall see later in this unit. Monoprotic, diprotic, triprotic, and polyprotic acids. Consider these two acids, HCl and HNO3. Both of these are able to lose one proton only. An acid that has one proton available to donate is called a monoprotic acid. So both HCl and HNO3 are monoprotic acids. Now consider this acid, H2SO4. It's called sulfuric acid. Notice it has two H atoms at the beginning of the formula. Acids that have two protons they can donate are said to be diprotic. So H2SO4 is a diprotic acid. However, when diprotic acids like H2SO4 are added to water, they do not lose both of their protons at once. They do it in steps, losing one proton at a time. In the first step of the reaction of H2SO4 and water, the H2SO4 loses one proton to water. So the water is converted to H3O+, or hydronium. Because the H2SO4 is losing an H+, it means it's losing one H atom and one positive charge. This gives us HSO4 with a minus charge. HSO4- is called a hydrogen sulfate or bisulfate ion. Notice that HSO4- has one hydrogen it can lose. So in the second step of the ionization of sulfuric acid, the HSO4- will react with water and donate its proton to water, which would produce another hydronium ion. The HSO4- loses a proton, so it loses one hydrogen and one positive charge. So it will be left as SO4, and losing one positive charge will cause its charge to go down one, from -1 to -2, or 2-. The product SO4 2- or sulfate ion does not have any hydrogens to donate, so this is the last step in the ionization of sulfuric acid. The double arrow here implies that there is an equilibrium. This reaction does not go to completion. Whereas in the first step of the ionization of sulfuric acid, there is a single arrow, which means this step goes to completion. 100% of the sulfuric acid is converted to hydronium and hydrogen sulfate ions. Now we'll look at phosphoric acid. We see that it has 3 H's at the front of its formula, which means it has 3 protons it can lose. For that reason, phosphoric acid is called a triprotic acid. When it's combined with water, it doesn't lose all 3 protons at once, just one at a time. In the first step, 1 proton is transferred to a water molecule, so it produces 1 hydronium ion. Because it loses 1 H and 1 positive charge, the other product would have 2 H's and a charge of -1. H2PO4- is called the dihydrogen phosphate ion. We see it still has 2 protons it can donate. In the second step, the H2PO4- ion loses one of its protons to water, so it produces another hydronium ion. And since this loses 1 H and 1 positive charge, the other product would be HPO4 2-. This product is called the monohydrogen phosphate ion. We can see that it has 1 proton available to donate. So in the last step, the HPO4 2- donates a single proton to water, producing another hydronium ion. And because it loses 1 H and 1 positive charge, the final ion that it forms is just PO4 3-. This is simply called the phosphate ion. Polyprotic acid is just a general term for any acid that can donate more than 1 proton. Examples could be carbonic acid, which is diprotic, phosphoric acid, which is triprotic, and pyrophosphoric acid, which has 4 protons it can donate.